Welcome to The Explainer. I am absolutely pumped you're joining me today because we are looking at one of the most downright fascinating objects in our entire solar system. I'm talking about Jupiter's moon, Europa. So consider this your comprehensive mission briefing and study guide. Whether you're a future planetary scientist, an armchair astronomer, or just, deeply curious about where we might actually find extraterrestrial life, you are absolutely in the right place. Today, we're taking a vertical journey. We're going to start from Europa's icy exterior, dive way down deep into its hidden ocean, and pull all the way back up to its exosphere. Here is our flight plan for today's briefing. We've got 1. The smoothest alien world, 2. Magnetic clues to hidden oceans, 3. The tidal heating engine, 4. Chemistry for potential life, 5. Timeline of Europa's atmosphere, and 6. Future mission study guide. Let's get right into it.
Section 1. The smoothest alien world, an icy mystery.
Okay, let's dive into this because this is a massive planetary puzzle. Europa sits in a really busy, chaotic neighborhood full of space debris. By all accounts, it should be heavily pockmarked, looking a whole lot like our own Earth's moon. But it doesn't. It is essentially the smoothest solid object in the entire solar system. You're not going to find towering mountains or deep impact craters here. Why? Well, because Europa possesses an active ice shell that literally constantly resurfaces itself. When meteors hit, or when the ice fractures into those beautiful long dark streaks called lineae that we see from orbit, warmer ice or liquid from below eventually wells right up and freezes over. It acts almost like a giant cosmic Zamboni, wiping the geological slate clean every 20 to 180 million years. And that incredibly smooth, active surface, that's our very first major clue that something highly dynamic is happening down below. Section 2. Magnetic clues to hidden oceans. What lies beneath? Back in the late 1990s, when the Galileo space probe orbited Jupiter, it took some magnetic readings that kind of changed everything. You see, Earth has an intrinsic magnetic field, right? Generated by the molten iron churning around in our core. Europa, however, doesn't generate its own magnetic field like that at all. Instead, Galileo's data showed that Europa has an induced magnetic field. As Jupiter's massive rotating magnetic field sweeps over Europa, it creates a secondary magnetic field right around the moon. Now, for this to happen, the laws of physics dictate there literally must be a global layer of highly electrically conductive material just beneath Europa's crust. And out there in the outer solar system, the most plausible highly conductive material is a massive global ocean of salty, liquid water. This magnetic signature was the absolute smoking gun. Now, what's truly mind-boggling here is the sheer, unimaginable scale of this liquid environment. When we talk about Europa's subsurface ocean, we aren't talking about a couple of subterranean puddles. No way. We are talking about a global ocean estimated to be up to 100 kilometers. That's over 60 miles deep. Even though Europa is slightly smaller than our own moon, this deep global layer means Europa contains 2 to 3 times the total volume of liquid water found in all of Earth's oceans combined. Just let that sink in for a second. A tiny ice ball way out in the outer solar system holds more water than the great blue dot of Earth.
Section 3. The tidal heating engine, keeping the ocean liquid.
But wait a minute. Europa's surface temperature is about minus 260 degrees Fahrenheit. Space is absolutely freezing. So how on Earth, or how on Europa, does this massive subterranean ocean actually stay liquid? Well, let's look at the astrophysical engine responsible for this. It all comes down to gravity and a really cool phenomenon called orbital resonance. Europa is locked in this intricate gravitational dance with Jupiter and its neighboring moons, Io and Ganymede. Every single time Europa orbits Jupiter, these other moons line up and give it a slight gravitational tug. Think of it exactly like giving a kid a rhythmic push on a playground swing. If you push at exactly the right moment, the swing just naturally goes higher. These regular rhythmic gravitational pushes force Europa's orbit to be slightly eccentric, kind of oval-shaped, rather than perfectly circular. This means Europa is constantly moving closer to and then further away from Jupiter's immense gravitational grip. And this brilliantly illustrates the concept of tidal flexing. Because Europa's distance from Jupiter keeps changing due to that eccentric orbit, the gravitational pull on the moon changes right along with it. As it gets closer to Jupiter, the giant planet's gravity physically stretches Europa, elongating it. Then, as it moves further away, the moon relaxes back into a sphere. Imagine taking a cold, stiff piece of dough and kneading it vigorously with your bare hands. The friction from that constant stretching and squishing actually warms the dough right up. The exact same thing happens to Europa's rocky interior and its thick ice shell. This tidal flexing generates immense internal heat through pure friction, and that, my friends, is the engine that prevents this massive ocean from freezing solid.
Section 4. Chemistry for potential life.
The ingredients.
Having a warm, liquid ocean is amazing, but water alone isn't going to cut it for life. You need the right chemical ingredients. For biology to actually thrive, it needs energy and chemical building blocks, like oxygen. But Europa's ocean is trapped under miles of solid ice, totally cut off from the atmosphere above. So how on Earth could oxygen get all the way down there? The answer is this absolutely fascinating three-step pathway. First up, Jupiter's intense magnetic field bombards Europa's surface with incredibly high levels of radiation. Second, this radiation blasts the surface ice, literally breaking the water molecules apart into hydrogen and oxygen, a process scientists call radiolysis. The lighter hydrogen mostly escapes into space, but the heavier oxygen sticks around. Third, through the constant churning, cracking, and potential subduction of Europa's active ice plates, that surface oxygen is slowly, steadily dragged down through the ice and deposited right into the ocean below. This provides a huge potential energy source for biological life.
And the chemistry gets even richer when we start looking at the weird discoloration on Europa's surface. Those reddish-brown streaks we've seen from space, they aren't just dirty ice. Spectrographic data tells us those surface fractures are coated in salts, specifically things like magnesium sulfate, which is essentially sea salt that is likely bubbled up from the ocean below. On top of that, the intense radiation bakes the surface, generating tholins. These are abiotic organic compounds that can act as the absolute crucial building blocks for early prebiotic chemical processes. We also see deposits of carbon dioxide and sodium chloride. It's an astrobiologist's dream scenario. We have the water, we have the heat, and we have a highly complex chemical soup that could, just maybe, support life.
Section 5. Timeline of Europa's atmosphere. Discoveries above.
Let's trace this timeline to see how our scientific understanding has really evolved. Now, Europa doesn't have a thick, comfy atmosphere like Earth. It's a very tenuous exosphere, but it is highly dynamic. Back in 1995, the Hubble Space Telescope made the groundbreaking discovery that Europa actually has a thin oxygen atmosphere, generated by that exact radiation bombardment we just talked about. Then in 1997, as the Galileo probe slipped right behind Europa, its radio signals passed through the atmosphere, definitively proving the existence of a charged, ionized layer. But hey, science is always refining its models, right? Fast forward to March 2024, and astronomers analyzing brand new data reported that Europa's surface might actually produce significantly less oxygen than we previously inferred. This timeline shows you exactly why we need to send new, highly upgraded instruments back to the Jovian system to get the best data possible.
Section 6. Future Mission Study Guide. Preparing for the Clipper.
And that leads us perfectly into the final phase of our briefing. If you were taking notes, here is your definitive habitability study guide. We've confirmed the main pillars. Water? Check. It's present in a massive subsurface ocean. Energy? Check. Provided by the intense heat of tidal flexing. Chemistry? Definitely active, with surface oxygen, tholins, and sea salts interacting. But I do have to add a really crucial update here. Recent geological models from 2026 actually suggest that Europa's rocky seafloor might be geologically quiet today. If the rocky crust down there is just too strong to be fractured by current tidal forces, it means we might not have highly active hydrothermal vents like the ones we see teeming with life on Earth. That could severely limit the chemical energy available for chemoautotrophic life at the bottom of the ocean. It's a sobering reminder that while Europa definitely has the ingredients, the recipe for life might be facing some steep energy challenges.
So, to solve these deep mysteries, NASA launched the Europa Clipper in October 2024. And the most crucial point is how this incredible machine is actually going to gather its data. The Clipper won't orbit Europa directly, mostly because Jupiter's intense radiation belts would completely fry it. Instead, it's going to orbit Jupiter and conduct 45 daring low-altitude flybys right past Europa. During these swoops, it's going to use ice-penetrating radar to finally figure out exactly how thick that ice shell is. It'll scan the horizon for active water vapor plumes, literally tasting the ocean water if it happens to be venting out into space. Ultimately, its primary objective is to map the surface, investigate overall habitability, and scout the absolute best locations for a potential future lander mission. Which really leaves us with this final, profoundly deep question to ponder. We are actively exploring a world that has the water, the heat, and the chemistry. If the Europa Clipper probe peeks beneath that incredibly smooth icy shell and discovers the definitive active ingredients for life right here in our own cosmic backyard, how will that completely change our understanding of our place in the universe? If life can take hold in the dark, intensely irradiated depths of Jupiter's gravity well, it strongly suggests the cosmos might literally be teeming with biology. Keep your eyes on the Clipper mission, everyone. The answers are out there, just waiting in the dark, warm waters of Europa. Thanks so much for joining me on this explainer, and remember,